Hello, today we are going to cover bisectors of triangles. You guys will be able to identify and use perpendicular bisectors as well as angle bisectors in these triangles. Our new vocabulary is perpendicular bisectors as well as concurrent lines, point of concurrency, circumcenter, and incenter. So, perpendicular bisectors, we have a new theorem plus its converse for these. A perpendicular bisector theorem states if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So if C is on this perpendicular bisector, notice we know it's a perpendicular bisector because it crosses at 90 degrees. It also bisects, that means it cuts the segment in half. So not only do we have angle bisectors, we also have segment bisectors. Kind of makes D the midpoint. If this happens, then we know that the distance from AC and the distance from CB is equivalent. We also have the converse of that. If we know, in this case, E is equidistant from A and B, then we know that this line here is the perpendicular bisector to the segment AB. So we can use that to solve some things. So we have the perpendicular bisector theorem here. We have a line going through at 90 degrees and creating two congruent segments. That means that BC is 8.5 because of the perpendicular bisector theorem. Similarly, using the converse though this time, we have a line going through at 90 and these guys are congruent, so that means XY has to be equal to 6. Pretty simple. Back to the normal perpendicular bisector theorem, we have perpendicular, we have it bisecting the segment PR. That means these guys are congruent, so set them equal and solve. So x equals 2. Plug that back in for PQ to finish solving. And PQ must equal 7 units in length. Alright, so that is the end of just talking about perpendicular bisectors. Now we're going to use it in our circumcenter theorem. So the perpendicular bisectors of a triangle intersect at a point called the circumcenter that is equidistant from the vertices of the triangle. So this point here, crazy thing is, no matter what kind of triangle we have a circumcenter, is made from these perpendicular bisectors, so 90 degrees, and they cut the segment in half. It's made up of 3 of those. If you notice, we have 90, and then we have congruent segments from each larger segment. If we know that, using the circumcenter idea, it says that from this point to the vertices is also congruent. So PC is congruent to PB, is congruent to PA. Pretty crazy there. So the location of the circumcenter, like I said, you have a circumcenter in every triangle, is based on the type of angles in the triangle. So if you have an acute triangle, the circumcenter is inside the triangle. If you have an obtuse triangle, the circumcenter is outside the triangle. And if you have a right triangle, it is on the triangle. It's on one of the sides, or on the hypotenuse. Now, it's kind of hard to visualize those, and it's also very hard to draw them. So if you would like to see a visual, on page 326 of your book, you can see all of those inside, outside, and on the triangle ideas. For now, though, we have to determine if the circumcenter of each triangle is inside, outside, or on the triangle, and explain. So I kind of have written out a little prompt here for my explanation and whether it's inside, outside, or on. So I just have to fill in these blanks. I know it's an obtuse triangle. So the circumcenter is outside the triangle. For part B, it's an acute triangle. So the circumcenter is inside the triangle. And it's as easy as that. So circumcenter is just a quick recap. They have segments congruent like these. And because we know it's a circumcenter with perpendicular bisectors coming together, we know from that concurrent point, or point of concurrency, that point P, in this case, out to the vertex, each of those are congruent. So there will be a question on your homework that asks you to label a picture of a circumcenter triangle. You just have to draw out the tick marks just as they are here. You'll do one for an incenter too, and we'll go over that in just a little bit. So angle bisector, the angle bisector theorem tells us if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So this point F is on this bisector BF. We know it is equidistant from the sides of the angle. If you remember, we take our perpendicular distance, so these must be perpendicular, meaning that DF and EF are equal, the same length. So by angle bisector theorem, those are the same. You could also think of this as like, let's see here, we would have side, so we would have angle, side here. So if you really wanted to, you could think of these as triangle congruences. But now we have the angle bisector theorem, so you just know these are congruent based on that. We also have the converse. So if we are given that DF and FE are congruent with this 90 and this 90, we could do hypotenuse leg theorem to state that these angles are congruent. And then we know that this bisects. All right, so we're going to use that idea. I see these 90s, that means we have a perpendicular distance, cool, and we have these congruent, which means that these guys are congruent, making DB 5 units long. Similarly here, but now we're using the converse of the angle bisector theorem. These two must be congruent, so the measure of WYZ is 28 degrees. And once again, you can just throw in a little bit of algebra here. You just set them equal to each other and solve. So x is going to equal 3. Plug it back in for QS. So 11 is the length of QS. That also means that is the length of SR. Now we have our incenter. Notice how it looks very similar to circumcenter, but it's not the same. The incenter deals with angle bisectors. So the angle bisector of a triangle intersects at a point called the incenter. So now, this time we know that these angles are congruent, and these angles are congruent, and these angles are congruent to each other as well. We don't know anything about like saying that that's the midpoint. We don't know that. Similar to the circumcenter though, we now know that that point of concurrency means that from that point down to the side is congruent. So on your homework, you're going to have one that states label the tick marks of an incenter triangle. You'll want to do the congruent sides, congruent angles, as well as the congruent from the concurrent point down to the sides are congruent. And you'll label it like that. So now we can use that information to solve for some things. So we know S, the point S is the incenter of triangle M and P. We need to find ST. The thing is, we don't know anything about those congruent pieces. But if we take a close look, we do have this triangle here. And we have a leg length, and we have the hypotenuse. And we can solve for that side, which happens to be congruent for ST. So if we do the Pythagorean theorem, I'm just going to solve this out. You can follow along. A must equal 6, and if 6 is the measure of that side length, and SU is congruent to ST, ST must also equal 6. We have to kind of go a little roundabout, but once you get there, you get there. For the measure of SPU, once again, we also have to go a little roundabout. I like to think about the whole big triangle. And because this is the incenter, I know those two angles are congruent. And these two are congruent. And these two are also congruent to each other. So this one is 31, and this one is 28. And these ones I'm going to label both x. And then I can just set up and solve an equation. So I go ahead and solve. I combined my 31 and my 28s. You could skip that step and go ahead and just add them all together, but it was easier for me to do it that way. Easier numbers to add. To get 62, so then I go ahead and divide by 2, and x will equal 31. And then I go ahead and I know that the measure of SPU is equal to 31 degrees. I'll give you a second. You can try the next one on your own, and then I'll scroll up. So go ahead and pause me and try the next one. Alright, hopefully you got these as your solutions. It's very similar to the last example, and you should be good to go.